Welcome to Yashil Chemistry Academy for CBSE 12 Chemistry. Today, we will see the lesson solution. Concentration of solution, we will take it up today. We will see various ways of representing the concentration of solution. And then we will also do some numerical based on concentration of solution. Right. Solution is a homogeneous mixture of two or more substances. Concentration of solution can be represented in many ways. We will see some ways of representing concentration of solution. One is mass percentage. It is the amount of solute present in 100 gram solution. Mass percentage is equal to mass of solute divided by mass of solution into 100. If we say 10% by mass of aqueous solution of sodium hydroxide, 100 gram solution contains 10 grams of sodium hydroxide solute and 90 grams of water solvent. Volume percentage. It is generally used when two liquids combine together to give you a solution. Example, 5% by volume of aqueous solution of ethanol. Volume percentage is equal to volume of solute divided by volume of solution into 100. 5% by volume of aqueous solution of ethanol. In 100 centimeter cube solution, 5 centimeter cube is ethanol, which is a solute, and 95 centimeter cube is water, which is a solvent. Then mole fraction. It is the number of moles of component divided by total number of moles in this solution. For example, I want to find out the mole fraction of 4 grams of sodium hydroxide dissolved in 972 grams of water. First, find out the number of moles of solute and solvent. Number of moles of solute sodium hydroxide, mass of sodium hydroxide divided by molecular mass of sodium hydroxide. 4 by 40, 0.1 here. Same number of moles of solvent, water, mass of water divided by molecular mass of water. 72 by 18, 4 here. So total number of moles is 4 plus 0.1, 4.1 here. Mole fraction of NaOH, number of moles of NaOH divided by total number of moles. 0.1 by 4.1, 0.024. Mole fraction of water, number of moles of water is 4 divided by total number of moles 4.1. 4 by 4.1, 0.976. Always, if you add all mole fraction, it will become equal to 1. Part per million. It is normally used when a gas is dissolved in a solvent to give a solution because solubility of a gas in a solvent is very less here. It is the amount of solute present in 10 power 6 gram solution. Sea water contains 5.8 part per million oxygen. That means if I take 10 power 6 gram solution of sea water, it will have 5.8 gram of oxygen. Molarity and molality are two commonly used terms here. Molarity is the number of moles of solute present in 1 liter of solution or 1 decimeter cube solution. Molarity is equal to number of moles of solute divided by volume of solution in liters or decimeter cube. For example, 4 grams of sodium hydroxide dissolved in 200 ml solution. Number of moles of NaOH, mass of NaOH divided by molecular mass of NaOH, 4 by 40, 0.10 moles. Volume of solution in decimeter cube or liters, 200 centimeter cube divided by 1000, 0.20 decimeter cube. So molarity is equal to number of moles of methanol divided by volume of methanol in, number of moles of sodium hydroxide divided by volume of sodium hydroxide in decimeter cube. So 0.10 divided by 0.20. That is 0.50 mole per decimeter cube. Molarity equal to mass of solute divided by molar mass of solute into 1000 by volume of solution in centimeter cube. So 4 by 40 into 1000 by 200. That is 0.50 mole per decimeter cube. If percentage mass is given, percentage mass of solute divided by molar mass of solute into 10 into density. Example, molarity of 49% by mass of sulfuric acid having a density of 1.5 gram per centimeter cube. So 49 divided by 98 into 10 into 1.5, which is 7.5 mole per decimeter cube. Molality, it is the number of moles of solute in 1 kilogram of solvent. Number of moles of solute divided by mass of solvent in kilogram. Example, 4 grams of NaOH dissolved in 100 grams of water. Number of moles of NaOH, 4 by 40, 0.10 moles. Mass of water 100 by 1000, 0.10. So molality equal to number of moles of NaOH divided by mass of water, 0 in kilogram, 0.10 by 0.10, 1 mole per kilogram. Formula: mass of solute divided by molecular mass of solute into 1000 by mass of solvent, or percentage mass of solute divided by molecular mass of solute into 1000 by 100 minus percentage mass of solute. Example: concentrated sulfuric acid is 49% by mass. Determine its molality if the density of the solution is 1.5 gram per centimeter cube. So percentage mass of solute is 49 divided by molecular mass of solute 98 into 1000 divided by 100 minus 49. That is 49 by 98 into 1000 by 51. 9.80 mole per kilogram. Effect of temperature and concentration of solution. In a closed system, when the temperature is increased, mass does not change, but the volume of solution will expand here. Molality is number of moles of solute divided by mass of solvent in kilogram. So all mass terms are involved here. So molality does not change with the temperature. Whereas molarity, number of moles of solute divided by volume of solution in decimeter cube. Here, when you increase the temperature, volume will expand. Therefore, molarity of the solution will decrease as it increases in temperature is noticed. Solubility is the amount of solute that can be dissolved in a given amount of solvent at a particular temperature. Solid dissolves in a liquid to give a solution. Most of the process where solid dissolved in a liquid to give a solution is in the endothermic process. Delta H is greater than 0. That is, heat is absorbed by the system from the surrounding. Solubility increases when the temperature is increased. Therefore, solubility of a substance will increase as the temperature increases. In some cases, dissolution of solid in a liquid to give a solution is an exothermic process. In such cases, solubility will decrease when the temperature is increased. Pressure has no effect on the solubility of solid in a liquid to give a solution. Now let us see the formula for finding out the concentration of solution, and we will do some numerical based on it. Percentage mass of solute. Mass of solute divided by mass of solution into 100. Percentage volume of solute. Volume of solute divided by volume of solution into 100. Part per million, mass of solute divided by mass of solution into 10 power 6. Mole fraction of solute in a solution containing solute and solvent. Number of moles of solute divided by number of moles of solute plus number of moles of solvent. Mole fraction of solvent, number of moles of solvent divided by number of moles of solute plus number of moles of solvent. Always total mole fraction is equal to 1. Molarity, number of moles of solute divided by volume of solution in decimeter cube or liter. Or mass of solute divided by molecular mass of solute into 1000 by volume of solution in centimeter cube. Or molarity is equal to percentage mass of solute divided by molecular mass of solute into 10 into density of solution. 1 liter equal to 1 decimeter cube, which is equal to 1000 centimeter cube. Molality, number of moles of solute divided by mass of solvent in kilogram. Or I can write it as mass of solute divided by molecular mass of solute into 1000 by mass of solvent in gram. 1 kilogram equal to 1000 gram. In terms of percentage mass of solute divided by molecular mass of solute into 1000 divided by 100 minus percentage mass of solute. We'll do few numerical based on this. First one is based on percentage mass and part per million. A sample of drinking water contains 15 part per million chloroform, CHCl3 by mass. Express this in percentage mass. What is given is 15 part per million. That is, if I take 10 power 6 gram solution, 15 grams of chloroform is present. What is asked here is finding out the percentage mass. That is, how much of chloroform present in 100 gram solution. So I can write it as 10 power 6 gram solution contains 15 gram chloroform. 100 gram solution contains how much of chloroform? 15 into 100 by 10 power 6. 15 into 10 power minus 4 here. That is percentage mass of chloroform here. The next part of the question is find out the molality of the solution. Now percentage mass is known, molecular mass is known. So I can go for the formula. Molality equal to percentage mass by molecular mass into 1000 by 100 minus percentage mass. So 15 into 10 power minus 4 into 1000 by divided by 119.5 into 100 minus 15 into 10 power minus 4. 100 minus 15 into 10 power minus 4, I can take it as 100. So 15 into 10 power minus 4 by 119.5 into 1000 by 100, which is 1.256 into 10 power minus 4 mole per kilogram. Whenever you do the numerical, write the formula clearly, show the substitution clearly, write the answer with its unit. Unit also carry mass. Concentrated sulfuric acid is 49% by mass. Density of the solution is 1.5 gram per centimeter cube. Determine its molality and mole fraction of sulfuric acid in the solution. Molecular mass of sulfuric acid 98. Sometimes molecular mass will not be given to you in the exam because atomic mass of hydrogen, sulfur and oxygen is known to you. First method using the formula. Percentage mass of solute divided by molecular mass of solute into 10 into density. So 49 by 98 into 1.5 into 10, that is 7.5 mole per liter. Molality, percentage mass of solute by molecular mass of solute into 1000 divided by 100 minus percentage mass of solute. So 49 by 98 into 1000 divided by 100 minus 49. So it is equal to 9.80 mole per kilogram. Second method is from concepts here. 100 gram solution contains 49 grams sulfuric acid, 51 gram water. That is the meaning of 49% by mass of sulfuric acid. So molarity, mass of solute by molecular mass of solute into 1000 by volume of solution. That is the volume occupied by 100 gram solution. So 100 by 1.5, density is 1.5. That gives the volume of solution. Now substitute here. So 49 by 98 into 1000 by 100 by 1.5. That is equal 49 by 98 into 1000 into 1.5 by 100, which is equal to 7.5 mole per liter. Molality, mass of solute by molecular mass of solute into 1000 by mass of solvent. 49 by 98 into 1000 by 51, 9.80 mole per kilogram here. Mole fraction, number of moles of sulfuric acid divided by number of moles of sulfuric acid plus number of moles of water. Number of moles of sulfuric acid is 49 by 98, 49 grams of sulfuric acid, molecular mass is 98.50. Number of moles of water, 51 divided by 18. 51 grams of water divided by molar mass of water is 18, 2.83. Total number of moles is 3.33. So mole fraction of sulfuric acid, number of moles of sulfuric acid divided by total number of moles. 0.50 by 3.33, 0.150. Mole fraction of water is 1 minus mole fraction of sulfuric acid. 1 minus 0.150, 0.850. Concentrated nitric acid is 68% by mass. Density of the solution is 1.5 gram per centimeter cube. Calculate the volume occupied by 20 gram of nitric acid. I'll be using two formulas here. Number one, percentage mass by molecular mass into 10 into density. Number two, I'll be using the formula mass of solute divided by molecular mass of solute into 1000 by volume of solution. Same solution, so molarity is same here. I can equate the two equations and find out the volume occupied by 20 grams of nitric acid. Percentage mass by molecular mass in 10 into density, 68 by 63 into 10 into 1.5. That is it in terms of percentage mass. Then in terms of mass by molecular mass in 1000 by volume, that is 20 by 63 into 1000 by volume. So I can write 68 by 63 into 10 into 1.5 is equal to 20 by 63 into 1000 by volume of solution. So by using this equation, I can find out volume of solution is equal to 19.61 centimeter cube. Another method is from the concept here. See, I want to first find out what is the volume occupied by the 100 gram solution. 1.5 gram solution occupy a volume of 1 centimeter cube. That is the density given here. 100 gram solution occupy 100 by 1.5 centimeter cube. This is occupied by 68% nitric acid. That is 68 gram nitric acid. 68 gram nitric acid occupies a volume of 100 by 1.5 centimeter cube. 20 gram of nitric acid, what is the volume occupied? 100 by 1.5 into 20 by 68, which is 19.61 centimeter cube. Right. Now, one textbook numerical, sodium carbonate and sodium bicarbonate mixture containing 1 gram is completely neutralized by 0.1 molar HCl. Determine the volume of HCl needed if the mixture contains equimolar mixture of sodium carbonate and sodium bicarbonate. Molecular mass of sodium carbonate 106 gram per mole, sodium bicarbonate 84 gram per mole. So first you have to use the expression given here, equimolar mixture. That is same number of moles of sodium carbonate and sodium bicarbonate. That is the key word here. Mass of sodium carbonate x gram, mass of sodium bicarbonate 1 minus x gram. Number of moles of sodium carbonate, mass by molecular mass, x by 106. Number of moles of sodium bicarbonate, 1 minus x by 84. Number of moles are same, So I can write it as x by 106 equal to 1 minus 6 by 84. Using this equation, I can find out x here. X equal to 106 by 190, which is the mass of sodium carbonate. Number of moles of sodium carbonate, mass by molecular mass. So 106 by 190 into 1 by 106, which is 1 by 190 moles. So I know the number of moles of sodium carbonate is equal to the number of moles of sodium bicarbonate, which is equal to 1 by 190 moles. Second part, I want to find out how much of HCl is required by using the equations. Sodium carbonate plus 2 HCl. Na2CO3 plus 2 HCl gives 2 NaCl plus H2O plus CO2. 1:2 ratio. 1 mole of sodium carbonate requires 2 moles of HCl. 1 by 190 moles of sodium carbonate will require 2 times 2 by 190 moles of HCl. Other one is bicarbonate. NaHCO3 plus HCl gives NaCl plus H2O plus CO2. 1:1 ratio. 1 mole of sodium bicarbonate requires 1 mole of HCl. 1 by 190 moles of sodium bicarbonate requires same amount, 1 by 190 moles of HCl. Total number of moles of HCl is 1 by 190 plus 2 by 190, 3 by 190 moles here. Molarity equal to number of moles of HCl divided by volume of solution in decimeter cube. Now I know the number of moles of HCl, I know the molarity, so I can find out the volume of solution, right? 0.10 equal to 3 by 190 into 1 by volume of solution. So volume of HCl is equal to 3 by 190 into 1 by 0.10, which is 0.1578 decimeter cube or 157.8 centimeter cube. Now you see, finding out the molality from molarity here. Calculate the molality of 1 molar solution of NaNO3. Density of solution 1.25 gram per centimeter cube. Molar mass of NaNO3 is 85. First method using the formula. Molarity equal to percentage mass by molecular mass into 10 into density. Molecular mass is known to be, density is known to be. Molarity is given 1 molar. So I find out the percentage mass of solute. 1 is equal to percentage mass of solute by 85 into 10 into 1.25. Percentage mass I calculate, it is 6.8%. Then molality equal to percentage mass by molecular mass into 1000 by 100 minus percentage mass. So 6.8 by 85 into 1000 by 100 minus 6.8, 0.858 mole per kilogram. This is one method. Another method is from the concept here. When they say 1 molar NaNO3, it means 1 mole of sodium nitrate in 1000 centimeter cube solution, or 85 gram of sodium nitrate in 1000 centimeter cube solution. Find out the mass of 1000 centimeter cube solution. Density is given as 1.25 gram per centimeter. So 1.25 into 1000 is 1250 grams. Mass of solvent is mass of solution minus mass of solute. So 1250 minus 85, 1165 grams. So I find out the molality, mass of solute by molecular mass of solute into 1000 by mass of solvent, which is 85 by 85 into 1000 by 1165, which is equal to 0.858 mole per kilogram. Next one is from the molality to molarity. Calculate the number of moles of methanol in 5 liters of 2 molar solution. Density of solution is 0.981 gram per centimeter cube. So if I find out what is the number of moles in 1 liter, that is molarity, I can multiply by 5 to get the answer here. So molality equal to 2, which is equal to percentage mass of solute by molecular mass of solute into 1000 by 100 minus percentage. So by substituting the values, I can get the percentage mass of the solute here. 2 is equal to percentage mass by 32 into 1000 by 100 minus percentage mass. So percentage mass of solute comes out as 6.015. Here, that's the percentage mass. So molarity is percentage mass by molecular mass into 10 into density. So 6.015 by 32 into 10 into 0.981, which is 1.843 mole per liter. Number of moles in 5 liter solution multiplied by 5. 1.843 into 5, 9.215 moles. Another method is finding out the mass of 2 molar solution. 2 molar solution of methanol means 2 moles of methanol plus 1 kilogram of water. So 2 into 32 plus 1000, 1064 grams. Mass of 5 liter solution using the density 0.981 into 5 liters, that is 5000 centimeter cube, 4905 grams. 1064 grams has got 2 moles of methanol. 4905 grams of solution contain how much of methanol? So 4905 into 2 by 1064, which is 9.21 moles. Then solubility product. Solubility product is the product of concentration of ions each raised to the stoichiometric coefficient in a saturated solution at 298 Kelvin. Here, the solubility product of copper sulfide is given as 6 into 10 power minus 6. Find out the molarity of CuS in aqueous solution. CuS gives you Cu2 plus S2 minus. If we take 1 mole per liter of CuS, let us say it gives you X mole per liter of Cu2 plus and X mole per liter of S2 minus. So Ksb equal to concentration of Cu2 plus and concentration of S2 minus, which is X into X square, which is equal to 6 into 10 power minus 6. So by taking square root, X equal to 2.45 into 10 power minus 3 mole per liter. That's the answer for the numerical taken. Now let's see the last one. Calculate the mass of urea required in making 2.5 kilogram of 0.25 molar solution of urea. Molar mass of urea, 60 gram per mole. So 0.25 mole, first find out what is the mass of urea in 0.25 moles of urea. So that is 60 into 0.25, 15 gram of urea. Then we find out the mass of urea solution. 15 gram is urea, 1000 gram is water, 1015 grams. So 1015 gram solution, if I want to make, I need 15 gram of urea. 2.5 kilogram, 2500 gram solution if I require, I have to make 15 into 2500 by 1015, which is equal to 36.95 grams. Thank you all for listening to this video. Next class, we'll do Henry's law, application of Henry's law and numerical based on Henry's law. Make the best use of these videos. I'll be uploading videos for all the lessons. It will help you to score well in CBSE 12 board examination. Best wishes. Welcome to Yashil Chemistry Academy, Lecture 2. Today, we'll be seeing the Henry's law, application of Henry's law, and numerical based on Henry's law. Let us start. Henry's law. Basically, we discuss about the solubility of a gas in a liquid. Solubility of a gas in a liquid is a exothermic process. In 11th standard, you studied that the exothermic reactions are not favorable at a higher temperature. Therefore, solubility of a gas in a solvent decreases as the temperature increases. Whereas solubility of the gas in a solvent increases with the increase in pressure. As the pressure increases, solubility of a gas in a liquid will increase. As the temperature increases, solubility of a gas in a liquid will decrease. Now let us see the relationship between the solubility of the gas and the pressure applied above the solution. It is given by Henry's law. There are two ways of expressing Henry's law here, or stating Henry's law. First one is at constant temperature. With the increase in at constant temperature, solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. At constant temperature, solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. P is the partial pressure of the gas is equal to Kh, called as Henry's law constant, into mole fraction of the gas. Mole fraction is considered as solubility here. Mole fraction is considered as solubility. Therefore, you can say at constant temperature, solubility of a gas in the liquid is directly proportional to the partial pressure of the gas above the solution. Another way is, instead of using solubility, I can use the term mole fraction here. Mole fraction of the gas in a solution is directly proportional to the partial pressure of the gas above the solution. Mole fraction of a gas in a solution is directly proportional to the partial pressure of the gas above the solution. Of course, temperature should be maintained constant. Kh is called as Henry's law constant. Okay. Kh is known as Henry's law constant. So there are two ways of expressing Henry's law. P is equal to, that is partial pressure of the gas that we are going to apply above the solution, equal to Kh, Henry's law constant. It depends on temperature, into mole fraction of the gas, a mole fraction of the gas present in the solution. Okay. Let us say at constant pressure, given pressure, I'm taking a particular pressure and comparing the solubility of the gas here, right? So here P equal to KH into Henry's law constant into mole fraction of the gas here. When the KH value is higher, solubility becomes lesser here. Higher the value of KH, lesser is the solubility of a gas in the liquid here. KH is higher, lesser will be the solubility of a gas in the liquid here. Again, KH also depends on temperature. KH depends on temperature. As the temperature increases, value of KH will increase. As the temperature increases, value of KH will increase. Therefore, the solubility of a gas will decrease with the increase in temperature. That is the reason why aquatic life are more comfortable in cold water than in warm water. Reason is solubility of the gas decreases with the increase in temperature. This type of statement we can expect from assertion reasoning question. Assertion they will give aquatic species are more comfortable in cold water than in warm water. And then reason they will give some reason. Solubility of gas decreases with the increase in temperature. Or sometimes they give solubility of gas increases with the increase in temperature. So you have to find out first, you take it as assertion separately, reasoning separately. Make a tick. Assertion is right, reason is right, and both are related to each other. Or sometimes assertion may be wrong, sometimes reason may be wrong, or assertion reason may be right, but they are not related to each other. Based on this, you have to choose, give you a choice. Right? So this is the graph drawn, partial pressure and mole fraction of HCl. So you can see as the pressure increases, mole fraction increases. In other words, you can say as the partial pressure, the pressure applied on the solution increases, solubility of the gas has increased here. Right? So P equal to KH, that is Henry's law constant into mole fraction of the gas. Mole fraction of the gas is nothing but number of moles of gas divided by number of moles of gas plus number of moles of solvent. When the Ng, number of moles of gas is very less, then I can take Ng, number of moles of gas plus number of moles of solvent is equal to number of moles of solvent. In that case, I can write KH into number of moles of gas divided by number of moles of solvent here. That is mass of the gas, KH into mass of the gas divided by molecular mass of the gas into molecular mass of solvent divided by mass of solvent. Depending on the value of KH on the pressure applied, we decide where we have to take Ng plus N solvent. Number of moles of gas plus number of moles of solvent is equal to number of moles of solvent here. Right. Now let us see at a given pressure, we have seen higher the value of KH, lower is the solubility of the gas here. I have taken three gases here, oxygen, nitrogen, helium. Helium, KH value is 144.97 kilobar. Oxygen, 34.86 kilobar. Nitrogen, 76.48 kilobar. So helium has got the maximum KH value. So it has got the least solubility. And then oxygen has got the minimum KH value. Among three gases, minimum KH value. So you can say oxygen is most soluble in water when compared to helium and nitrogen. So solubility helium less than nitrogen less than oxygen here. So higher the value of KH, lesser is the solubility. Sometimes they'll give you the KH value. They'll ask you to compare the solubility. One word multiple choice question we can get here. They give the value and then give solubility of helium less than nitrogen less than oxygen. And they give different combination. You have to find out which is correct here. There's a graph solubility versus partial pressure. Here you can see helium minimum solubility. Then nitrogen higher solubility. Oxygen still higher solubility. Again, solubility increases as the partial pressure increases. Right. Now let us see some of the application of Henry's law. Gases dissolves in a solvent, let us say in water, at high pressure and low temperature. High pressure and low temperature. That is the reason why soda water is made by dissolving carbon dioxide in water. Here, it is carried out at a high pressure. Higher pressure, it is packed in a bottle at a higher pressure. Solubility of carbon dioxide in soda water is increased by dissolving the gas at higher pressure. Next, you will see when you go deep in the sea here. See, normally swimmers, they go deep in the sea. Scuba divers, they go deep in the sea here. When you go deeper and deeper, the pressure will increase. When the pressure increases, what happens? Solubility of the gas will increase. Pressure increases, solubility of the gas will increase. Right? So what will happen? More nitrogen will dissolve in the blood. More nitrogen will dissolve in the blood here. So when after completing the diving, etc., they come to the surface here. They come to the surface, the pressure will decrease. When the pressure decreases, solubility will decrease. The pressure is decreasing, solubility will decrease. So what will happen? The excess of nitrogen, it will form bubbles of nitrogen gas will be formed in the blood here. The blood bubbles of nitrogen gas will be formed here. This will block the capillaries. When the capillaries are blocked, we get a pain called bed here. We get a pain here that's called as bed here. So that is one of the applications of Henry's law. So we have to reduce the concentration of N2 gas in the air. We have to reduce the concentration of N2 gas in the air. So scuba divers use tank containing a mixture of 11.7% helium. So some helium is added here. 56.2% nitrogen and 32.1% oxygen here. Right? So nitrogen percentages decrease here. Normally air contains 79% by mass of nitrogen. Here it is 56.2% nitrogen percent here. Helium, of course, the solubility is very less. So I'm adding helium in place of nitrogen. Some nitrogen is replaced with helium here. 11.7% helium, 56.2% nitrogen, and 32.1% oxygen here. So this is the application of Henry's law. Now let us say when you go higher up in the higher altitude, say when you are climbing the mountain, partial pressure of the gas will decrease. The pressure of the gas is going to decrease. So what happens? Solubility of oxygen will decrease. So solubility of oxygen decreases, amount of oxygen in the blood will decrease. That is, low blood concentration of oxygen in the blood will be there. So when the oxygen availability becomes lesser, we become weak and unable to think clearly. Our thinking is affected here. These symptoms are called as anoxia. These symptoms are known as anoxia. So these are some of the applications of Henry's law. Now let us see numerical based on Henry's law. Partial pressure of the gas is equal to Kh into mole fraction of the gas. That is Kh into number of moles of gas divided by number of moles of gas plus number of moles of solvent. In some cases, number of moles of gas plus number of moles of solvent can be taken as number of moles of solvent. First question, how many millimoles of N2 gas would dissolve in 1 liter of water at 293 Kelvin? Pressure exerted by N2 gas is 0.987 bar. Kh value for N2 is 76.4 kilobar. That is 76.4 into 10 power 3 bar. Very high value of Kh here. So I have written partial pressure of nitrogen is equal to Kh into number of moles of nitrogen plus number of moles of water. Number of moles of water is 1000 by 80 because 1 liter of water, density of water is 1 gram per centimeter cube. So 55.56 is the number of moles of water. So number of moles of nitrogen is very less when compared to number of moles of water. So I can take it as partial pressure of nitrogen equal to Kh into number of moles of nitrogen divided by number of moles of water. Right. So 0.987 equal to Kh value is 76.4 kilobar converted into bar into 10 power 3 into number of moles of nitrogen divided by 55.56. By calculating, I get 0.717 into 10 power minus 3 moles here. But here the answer asked here is in millimoles. So multiply by 1000. 0.717 into 10 power minus 3 into 10 power 3. That is 0.717 millimoles of nitrogen is present here. Next is partial pressure of ethane over a saturated solution containing 6.56 into 10 power minus 2 gram of ethane is 1 bar here. What will be the partial pressure of the gas if it contains 5 into 10 power minus 2 grams of ethane? So here the grams is decreasing. What will be the pressure here? There is an inverse proportionality between the amount of gas present and the pressure. Yeah, you just see. Sorry, so there's a direct proportionality between the amount of gas present and the pressure here. You'll just see partial pressure of gas is proportional to the mass of the gas dissolved. That is directly proportional here. As the partial pressure increases, mole fraction will increase, number of moles of gas will increase, so the mass is going to increase here, right? At 1 bar pressure, 6.56 into 10 power minus 2 grams of ethane exerts a pressure of 1 bar here. Then we have to find out what will be the pressure exerted when 5 into 10 power minus 2 grams of ethane is dissolved. So you can divide one by the other. 1 by P is equal to 6.56 into 10 power minus 2 by 5 into 10 power minus 2. So pressure is equal to 5 into 10 power minus 2 by 6.5 into 10 power minus 2, which is 0.769 bar. We'll once again see when the gas dissolved is 6.56 into 10 power minus 2 grams, pressure exerted is 1 bar. What will be the partial pressure of the gas if it contains 5 into 10 power minus 2 grams of ethane? So partial pressure and mole fraction directly proportional. Therefore, we can say partial pressure and mass of the gas is directly proportional here. So 6.56 into 10 power minus 2 grams exert a pressure of 1 bar. So 1 bar is proportional to 6.56 into 10 power minus 2. 5 into 10 power minus 2, what is the pressure we have to find out? So divide one by the other. 1 by B equal to 6.56 into 10 power minus 2 divided by 5 into 10 power minus 2. So I can find out the pressure, which is equal to 0.769 bars. Solubility of H2, standard question, H2S in water is 0.195 mole at STP, standard temperature and pressure. Calculate KH. See, first we have to look at the term here. Molality is given. Molality means number of moles of solute in 1 kilogram of solvent. Here it is, water is the solvent. So 0.195 moles of H2S present in 1 kilogram of water. That is the meaning. So number of moles of H2S is known to be 0.195 here. Number of moles of water, 1000 by 80, 55.56 here. Standard pressure is 1.013 bar. So KH I'm going to give it in bar, so I have taken the standard pressure of 1.013 bar. In case that has the KH in atmosphere, we take it as 1 atmosphere here, right? So partial pressure of H2S equal to 1.1013 bar here, right? That's what we have taken here. Now let us see. So 1.013 equal to KH into number of moles of H2S divided into number of moles of H2S plus number of moles of water. 0.195 is the number of moles of H2S divided by 0.195 plus 55.56. Here I am not neglecting the number of moles of solute here. I am not neglecting the number of moles of solute because it's known to me and it is not negligible here. So when I am substituting the values, KH is equal to 289.64 bars here. So one thing you have to note here, the number of moles of solute plus number of moles of solvent is not taken as number of moles of solvent. Number of moles of solute is also taken into account here. KH for CO2 in water is 1.67 into 10 power 8 Pascal at 298 Kelvin. Calculate the mass of CO2 that can be dissolved in 500 ml of water at 2.5 atmosphere at 298 Kelvin. Temperature is same, pressure is changing here, right? So again, partial pressure of CO2 is equal to KH into number of moles of CO2 divided by number of moles of CO2 plus number of moles of water. So number of moles of water is 500 by 18, 500 ml here. So 500 grams, molecular mass is 18, 27.78 here. Here you look at the KH value is very high. Therefore, I can take number of moles of CO2 plus number of moles of H2 as number of moles of H2. Number of moles of solute can be neglected in the denominator here. So here, pressure exerted now is 2.5 atmosphere. Convert it into Pascal here because KH is given in Pascal. 1 atmosphere is 1.013 into 10 power 5 Pascal. So 2.5 into 1.013 into 10 power 5 Pascal is equal to 1.67 into 10 power 8, which is KH value, into number of moles of CO2 divided by number of moles of CO2 plus 27.78. I take it as 27.78 here. So 2.5 into 1.03 into 10 power 5 is equal to 1.67 into 10 power 8 into number of moles of CO2 divided by 27.78. So denominator, I neglected the value of number of moles of CO2 here. So by using this, I can find out the number of moles of CO2, which is 0.0703 moles. But here mass of CO2 is as, so multiply by molecular mass, which is 44. Molecular mass of CO2 is 44. So 0.0703 into 44, 3.093 grams of carbon dioxide is dissolved in water at 2.5 atmosphere. This is the last one. Air is a mixture of gases, contains 20% by volume of oxygen gas and 79% by volume of nitrogen gas at 298 Kelvin. Water is in equilibrium with air at a pressure of 10 atmosphere. KH for O2 and N2 at 298 Kelvin is 3.30 into 10 power 7 millimeter and 6.51 into 10 power 7 millimeter respectively. Determine the composition of the gas in water. 1 atmosphere is equal to 760 millimeter pressure here. 1 atmosphere is equal to 760 millimeter pressure here, right? So here what we are going to use, we are going to use two formula. Dalton's law of partial pressure. Partial pressure of the gas is equal to total pressure into mole fraction of the gas. Partial pressure equal to total pressure into mole fraction of the gas. That is the first one. Second one is partial pressure of the gas is equal to KH into number of moles of gas divided by number of moles of gas plus number of moles of solvent here. These are the formulas we are using here. First, I am going for the Dalton's law of partial pressure. Partial pressure is equal to total pressure into mole fraction here, right? So mole fraction of O2 and mole fraction of N2 I have to find out here. So let us say it is given 20% by volume of O2, 79% by volume of N2 here. So I can take it as number of moles of O2 is 20 divided by total is 20 plus 79. 20 by 99 is the mole fraction of oxygen. Mole fraction of N2, 79 divided by 20 plus 79. 79 by 99 is the mole fraction of N2 here. So I can find out the partial pressure. Mole fraction into total pressure. Total pressure is given as 10 atmosphere. So 10 into 20 by 99, 200 by 99 atmosphere. Partial pressure of nitrogen is 10 into 79 by 99, 790 by 99 atmosphere. So I know the partial pressure of oxygen, partial pressure of nitrogen now, right? Now in water I am coming in, right? Water 200 by 99 equal to KH into, I'm looking for oxygen. So pressure is 200 by 99, KH into mole fraction of oxygen. KH is 3.3 into 10 power 7 given as millimeter here. So I have to convert it to atmosphere. 760 millimeter is 1 atmosphere. So I'm dividing it by 760. So 200 by 99 equal to 3.3 into 10 power 7 by 760 into mole fraction of oxygen. So by calculating, I'm finding out mole fraction of oxygen as 4.653 into 10 power minus 5 here. Next, mole fraction of nitrogen. 790 by 99 is the pressure, partial pressure of nitrogen. KH value is 6.51 into 10 power 7 in millimeters. So divided by 760 to make it into atmosphere. Into mole fraction of nitrogen here, I've written wrongly as oxygen. It's mole fraction of nitrogen. Change it now. Yeah. Okay. Right. So mole fraction of nitrogen, I'm calculating it is 9.316 in 10 power minus 5. Here itself we can leave in terms of mole fraction because mole fraction itself is solubility. Or you want to convert it into percentage also, you can do. So I add both the mole fraction here. Mole fraction of nitrogen plus mole fraction of oxygen. That comes to 4.653 into 10 power minus 5 plus 9.316 in 10 power minus 5. That is 13.969 into 10 power minus 5. That is the total here, right? I want to find out the mole percentage of nitrogen. That is mole 9.316 in 10 power minus 5. That is the mole fraction of nitrogen divided by total 13.969 into 10 power minus 5 into 100. That comes to 69.69%. Oxygen 4.653 into 10 power minus 5 divided by 13.969 into 10 power minus 5 into 100. That comes to 33.31 here. Thank you. Hope you found the class interesting. Next class, we will see Raoult's law and then derivation, Raoult's law for a solution containing a non-volatile solute and a volatile solvent, and for a solution containing two volatile solvents. That part we will do. If time permits, we will go for numerical based on Raoult's law. Okay, that's what I have written. Next lecture, Raoult's law for a solution containing two or more volatile solvent. Second part, solution containing a non-volatile solute and a volatile solvent. Subscribe to my channel and make the best use of videos in your preparation for board examination. Thank you very much. Welcome to Yashil Chemistry Academy CBSE 12 Chemistry with Srinivas Murthy. Today we will discuss about Raoult's law. In this PowerPoint presentation, we will cover the following topics. Number one, Raoult's law for a solution containing two or more volatile solvents. Raoult's law for a solution containing a non-volatile solute and a volatile solvent. Then, what is the meaning of ideal solution? Conditions for a solution to be ideal. Then non-ideal solution. Conditions for a solution to be non-ideal. Then positive deviation with example. Negative deviation with example. These are the things you'll be seeing. First, we'll start with Raoult's law for a solution containing two volatile solvents. Of course, two or more volatile solvents. I'm taking two volatile solvents here, right? Okay. So I have taken two volatile solvents, let us say A and B. So I have taken a volatile solvent A. This is solvent A, pure solvent. And another solvent B here, another volatile solvent B here, solvent B I have taken. Right? Both are pure solvents. Vapor pressure of solvent A is P naught A, a pure solvent A. I have taken it as P naught A. Vapor pressure of pure solvent B, I have taken it as P naught B here. I am mixing it together to get a solution AB here. To get a solution AB. AB is the solution here. Now, in AB, partial vapor pressure of A is PA. And partial vapor pressure of B in AB is PB here. AB is the solution. By mixing two volatile solvent A and solvent B, I mixed it. Vapor pressure of pure solvent A is P naught A. Pure solvent B is P naught B. And in the solution AB, vapor pressure of solvent A is PA. And vapor pressure of solvent B is PB here. Right. It is found out that the PA, that is partial vapor pressure of A, in the solution AB is proportional to mole fraction of A. PB is proportional to mole fraction of B. This is the determination. PA is proportional to mole fraction of A. PB is proportional to mole fraction of B in the solution here. Now let us say, look at the statement of Raoult's law for a solution containing two or more volatile solvent here. This is the statement. In a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to its mole fraction in the solution. Once again, I'll tell you. In a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to the mole fraction of it in the solution here. Right? So PA is proportional to mole fraction of A. PB is proportional to mole fraction of B here. Right? Total pressure is PA plus PB here. P total pressure of this solution I want to find out. P total is equal to vapor pressure of A, partial vapor pressure of A in the solution AB plus partial vapor pressure of B in the solution AB here. PA we already seen, P naught A into mole fraction of A plus PB is P naught B into mole fraction of B. This is total pressure in the solution. So this is the solution we have seen. Total pressure of the solution is partial vapor pressure of A plus partial vapor pressure of B here. Already we have seen PA is proportional to mole fraction of A. Or I can write PA is equal to P naught A into mole fraction of A. Same way, PB is proportional to mole fraction of B here. Or PB is equal to P naught B into mole fraction of B. So P total is PA plus PB, which is equal to P naught A into mole fraction of A plus P naught B into mole fraction of B here. This is the for a solution here, right? Now let us see what will happen in the vapor phase. In the solution I have seen, I'm going for the vapor phase. Right? In vapor phase, we'll see what is the condition here. Vapor phase. Right. Let us say in the vapor phase, I take it as mole fraction of A. Mole fraction of A. I'm taking it as YA. And mole fraction of B. Mole fraction of B. I'm taking it as YB here. YA and YB. Now let us see how it is related. Mole fraction of the vapor pressure. YA is equal to PA by P total. Or I can write it as P naught A into mole fraction of A divided by P total. That is YA here. Same way, that is the mole fraction of A in vapor phase. YB, mole fraction of B in vapor phase. PB is equal to PB by P total. YB equal to PB by P total, which is P naught B into mole fraction of B divided by P total. This is the situation in the vapor phase. You will get numerical based on this, finding out the mole fraction in the solution as well as mole fraction in the vapor phase here. This is the equation we get in this case. This is for a solution containing two or more volatile solvent. So once again, I'll tell you the statement. For a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to its mole fraction. Now let us see the graph for an ideal solution or a solution containing two volatile solvents A and B here. X-axis mole fraction is given, Y-axis vapor pressure is given here. When I move from left to right, mole fraction of A is left extreme, A is 1, and mole fraction of A decreases and becomes 0 at the right here. Whereas mole fraction of B at the left extreme is 0 and it increases, become 1 at the right extreme. So at the left extreme, Y-axis, we can see mole fraction of A is 1. Therefore, it's a pure solvent. It's shown as P naught A here. Same way, right extreme, mole fraction of B is 1. So it is P naught B, vapor pressure of pure solvent B here. And the dotted line shows the mole fraction at different, shows the vapor pressure at different mole fraction. That vapor pressure different mole fraction is shown. And the thick line you can see that shows the total pressure, PT equal to PA plus PB. So I can find out the total pressure at any mole fraction. I can also find out the partial vapor pressure of A and partial vapor pressure of B at any mole fraction we can find out here. Right. Now, I'm going for a solution containing a non-volatile solute and a volatile solvent here. See, for example, I've taken a pure solvent here, right? Pure solvent, A is taken. P naught A is the vapor pressure here. Let us see what do you mean by vapor pressure. So I have taken a closed system here. So the liquid, this is the liquid phase. Above the liquid phase, it is, we call it a vapor phase. So liquid phase and vapor phase I have taken here, right? Now, the liquid phase, the molecules have got different kinetic energy. I look at the average kinetic energy of the molecule. Now, the molecule which has got kinetic energy higher than the average kinetic energy evaporate and move to the vapor phase here. That is called as evaporation or vaporization. Molecules having higher kinetic energy than the average kinetic energy of the system moves to the vapor phase, that is evaporation here. Then the molecules, after some time, molecule in the vapor phase condenses, move back to the liquid phase, that's called as condensation. So both take place simultaneously. Evaporation and condensation take place simultaneously. At a particular stage, rate of evaporation becomes equal to rate of condensation. Rate of evaporation becomes equal to rate of condensation. Then we say an equilibrium is achieved there. An equilibrium is achieved. Vapor pressure exerted at equilibrium is called as vapor pressure of the liquid or vapor pressure of the solvent. It's given as P naught here. So vapor pressure exerted at equilibrium is the vapor pressure of the liquid. It is equal to P naught here, right? Now let us say I'm adding a same solution I have taken, same liquid I have taken. Right? Liquid A I have taken. I am adding a solute B, a non-volatile solute. Non-volatile solute. That is, B will not evaporate. Right? I can say sodium chloride, potassium chloride. There are non-volatile solutes. I am adding a non-volatile solute B here. So AB is the solution form here. AB is the solution form. Now what happens? The solute B and the solvent A, they will interact with each other. Of course, A and A interaction is already there. B and B also will interact. Now the AB interaction will start here. So, now the solute B interact with solvent A here in the solution. AB interaction taking place. Because of the interaction, the number of molecules going to the vapor phase will become lesser here. The number of molecules going to the vapor phase will become lesser here. So the vapor pressure will decrease here. Now let us say vapor pressure of the solution AB is P. P naught is the vapor pressure of solvent A. Vapor pressure of the solution containing a non-volatile solute is P. Right. So P naught minus P is called as lowering of vapor pressure. P naught minus P is known as lowering of vapor pressure. So for P naught minus P is the lowering of vapor pressure. For 1 atmosphere or 1 bar, 1 Pascal, whichever you want to take, P naught minus P by P naught. This is called as relative lowering of vapor. Relative lowering of vapor pressure. Right. That's what we are taking. So for a solution containing non-volatile solute, we have seen solvent, pure solvent is P naught. Solution is P containing a non-volatile solute. P0 minus P is lowering of vapor pressure. P0 minus P by P0 is called as relative lowering of vapor pressure. Now let us see the statement for Raoult's law for a solution containing a non-volatile solute and a volatile solvent. Here is the statement for a solution containing a non-volatile solute and a volatile solvent. Relative lowering of vapor pressure is equal to mole fraction of solute in the solution. Once again, I'll let you know, I'll tell you. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to the mole fraction of solute in the solution. Right? Here, A is the non-volatile solute, B is the solvent. Here, A is the non-volatile solute, B is the solvent. That's what I have taken here. So I can write P total is equal to P naught A, that is solute, into chi A, mole fraction of solute, plus P naught B into mole fraction of B. Right. This is what we get here. PA equal to P naught A into mole fraction of A plus P naught B into mole fraction of B. Now, the solute is non-volatile, so P naught A is negligible because it's a non-volatile solute here. So, I can write it as P total is equal to P naught B into mole fraction of B. That is solvent here. P naught solvent into mole fraction of solvent. If you want, I can write it as solvent. If you find it easier, P total is equal to P naught solvent into mole fraction of solvent. Solute contribution is negligible. I removed it here. Or I can write mole fraction of solute plus mole fraction of solvent is always equal to 1. So I can write it as P naught solvent into 1 minus mole fraction of solute, because total mole fraction is 1 here. 1 minus mole fraction of solute. Or it is P naught solvent minus P naught solvent into mole fraction of solute here. Mole fraction of solute here. That's what we have written. I am rearranging the equation now. I am rearranging the equation. Right? So and there we have seen P total equal to P naught solvent minus P naught solvent into mole fraction of solute here. So I am writing here P total is equal to P naught solvent minus P naught solvent into mole fraction of solute here. Right, solute. Or I'm taking it to the other side, rearranging the equation. P naught solvent into mole fraction of solute, right? I'm taking this side equal to P naught solvent minus P total here. Total. Or I can write mole fraction of solute, solvent and all we can remove now. P naught minus P by P naught here. Mole fraction is P naught minus P by P naught. This is what we get in this case here. P naught minus P by P naught is the mole fraction of solute. Now let us see the statement now once again. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute in the solution. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute in the solution. That's what we got in this case here. Mole fraction of solute is P naught minus P by P naught, which is relative lowering of vapor pressure is equal to the mole fraction of solute in the solution here. Now, mole fraction of solute means number of moles of solute divided by number of moles of solvent here. Generally, number of moles of solute plus number of moles of solvent is taken as such. It will not be written as number of moles of solvent. Most of the numerical done in the CBSE textbook, even in the exam, don't neglect it. But just for approximation, we can do it. Some numerical where the solvent is very high amount, then we can neglect. But generally, it is not neglected. For a dilute solution, N solute is very small when compared to N solvent. So denominator N solute plus N solvent can be taken as N solvent here, can be taken as N solvent. Then I can write it as P naught minus P by P naught equal to mass of solute by molecular mass of solute into molecular mass of solvent by mass of solvent. P naught minus P by P naught equal to mass of solute by molecular mass of solute into molecular mass of solvent by mass of solvent. But most of the cases, better you take it as mole fraction of solute is equal to P naught minus P by P naught is equal to mole fraction of solute for a solution containing a non-volatile solute and a volatile solvent, which is equal to number of moles of solute divided by number of moles of solute plus number of moles of solvent. Right? Later on in the next class, we will do some numerical based on vapor pressure of solution containing two or more volatile solvent, as well as vapor pressure of solution containing a non-volatile solute and a volatile solvent. Right? Now let us see, compare Henry's law and Raoult's law. Henry's law gives you the solubility of a gas in a solution. That's what you are seeing in Henry's law. There, partial pressure of the gas above the solution is equal to Kh, Henry's law constant, into mole fraction of gas in this solution. Here. Mole fraction of gas in this solution. As the partial pressure increases, mole fraction of gas in the solution also will increase. Raoult's law, for a solution containing two or more volatile solvent, Pa equal to P naught A in the mole fraction of A here. Pa, vapor pressure of A in the solution, AB, and P naught A is vapor pressure of pure solvent A, and Chi A is the mole fraction of solvent A in the solution, AB here. So Henry's law P gas equal to Henry's law constant Kh in the mole fraction of gas. Raoult's law Pa equal to P naught A in the mole fraction of A here, right? This is what we have seen in this case here, right? Now, Raoult's law becomes a special case of Henry's law when Kh and Pa are same. Kh and P naught A are same. When P naught becomes equal to Kh, then Raoult's law is a special case of Henry's law here. Raoult's law becomes a special case of Henry's law when P naught becomes equal to Kh here. That is, vapor pressure pure solvent becomes equal to Henry's law constant here. Vapor pressure pure solvent becomes equal to Henry's law constant, then Raoult's law becomes a special case of Henry's law here. Right. Now let us see, there are two types of solution we'll be studying. One is called as ideal solution, other one is known as non-ideal solution. Right. Ideal solution, we'll see solution which obeys Raoult's law over a wide range of concentration are called ideal solution. Solution which obeys Raoult's law over a wide range of concentration are called ideal solution. Of course, these two solvents should be non-reacting. Example, benzene and toluene. I'm mixing benzene and toluene to form a solution of benzene, toluene. Here, no hydrogen bond is formed, no hydrogen bond is broken here. So, no enthalpy change. Delta H mixing equal to 0. Because no bond is broken or no bond is made, no change in volume, delta V mixing is equal to 0. Interaction. Say if I take benzene, there's an interaction between the benzene molecules. Toluene, there's an interaction between toluene molecules. I have mixed together, I got a solution containing both the solvent, benzene and toluene. Now, let us say A is benzene, B is toluene, right? AB interaction in solution is nearly equal to AA or BB interaction. There's no change in the interaction here, or there's no change in the environment here. AB interaction is nearly equal to AA and BB interaction. So I can write PA equal to P naught A in the mole fraction of A, PB equal to P naught B in the mole fraction of B here. It's called as an ideal solution. So what our ideal solution means? Solution which obeys Raoult's law. If you write just Raoult's law, it's not sufficient. You should mention it as over a wide range of concentration are called ideal solution. Example, benzene, toluene. No hydrogen bond is formed or no hydrogen bond is broken here. So no enthalpy change, delta H mixing equal to 0. No volume change, delta B mixing equal to 0. PA equal to P naught A in the mole fraction of A. PB equal to P naught B in the mole fraction of B. AB interaction is nearly equal to AA and BB interaction. This is normally you'll get a reasoning question, assertion and reasoning question. You can expect it. They'll give a statement and then they give the reason. Whenever you do the assertion reasoning question, look at assertion separately, reasoning separately. Don't combine it at the same time. First look at the assertion separately and reasoning separately. If assertion is right, put a tick mark. If assertion is wrong, put a wrong mark. Then reasoning is right, put a tick mark. Otherwise, put a wrong mark. If both are right, then you see how they are correlated with each other. If they are correlated with each other, then you will arrive at the right answer. If you look at it, you will get a lot of confusion. First, look at the assertion. If it is right, put a tick mark. Wrong means put an into mark. Direction will be over. Reasoning, you look at it. Right, put a tick mark. Wrong means into mark. If both are right, then you see how they are correlated with each other. Then the reasoning given is correlated to assertion here. This is what we are going to check in assertion reasoning question. Now let us see for an ideal solution. Two solvents A and B are taken. They form a solution AB. No bond is made or no bond is broken. We are talking about hydrogen bond. No hydrogen bond is made or no hydrogen bond is broken here. X-axis, mole fraction, Y-axis, vapor pressure. One side, left extreme, mole fraction of B is 1. Right extreme, mole fraction of A is 1 here. So left extreme, Y-axis, P naught B. Right extreme, Y-axis, P naught A here. Then we have seen how the vapor pressure is changing. The blue line shows the partial pressure of A, solvent A. Green line shows the partial pressure of solvent B. The red line shows the vapor pressure of solution AB here. Red line, vapor pressure of solution AB. At any mole fraction, I can find out the total vapor pressure of the solution. Or partial vapor pressure of component B in the solution AB, or partial vapor pressure of component A in the solution AB. Anytime you can find out here. So this is a graph for an ideal solution. For an ideal solution, this is a graph we are seeing here. Right? Now let us see what do we mean by non-ideal solution. Non-ideal solution is the one which do not obey Raoult's law over the entire range of concentration of this solution. It's not obeying Raoult's law here. Either hydrogen bond is formed or hydrogen bond is broken here. That is the reason why it is not obeying ideal solution here. Say I'm taking in a binary solution of A, B. A is a solvent, B is another solvent. Mixing it together to give a solution A, B here. AB interaction is not same as AA or BB interaction. Here the interaction is different here. Environment has become different here. AB interaction is maybe more or less than the interaction shown in AA or BB, a solvent A or solvent B here. Right? Here new bond is made or broken here. So delta S mixing is not equal to 0 because there is some enthalpy change. Delta V mixing is also not equal to 0 here. Right? And PA is not equal to P naught A in the mole fraction of A. PB is not equal to P naught B in the mole fraction of B. This is non-ideal solution. You do not obey Raoult's law over the entire range of concentration. Either hydrogen bond is made or hydrogen bond is broken. Right? There are two types of deviation we'll be studying: positive deviation and negative deviation here. Right? First, we will see positive deviation. So I've taken ethanol here, C2H5OH. It's a solvent. C2H5OH. This is a solvent ethanol I have taken. Right. So it forms an intermolecular hydrogen bonding here. Intermolecular hydrogen bond here. This is one solvent here, right? Now I'm mixing it, adding N-hexane now. Yeah, N-hexane is added. Another solvent, N-hexane is added to form a solution here. Now what happens? N-hexane breaks the hydrogen bond in ethanol here. It comes in between the hydrogen bond. It is breaking the hydrogen bond in intermolecular hydrogen bond found by ethanol here. So N-hexane, another solvent, breaking the intermolecular hydrogen bonding formed in ethanol here. So here the bond has to be broken here. To break a bond, I have to supply energy. It's an endothermic reaction. So delta H mixing is greater than 0. Delta H mixing is greater than 0 because it's an endothermic reaction. Right? Now the bond is broken. So what happens? The molecules is more free now. Molecules are more free to vaporize here. It can vaporize easily. More freely it can move now. So delta V mixing is greater than 0 because it occupies more space here because the bonding is hydrogen bonding is broken here. It occupies more space. So delta V mixing is greater than 0. Now it can move more easily to vapor phase. So PA is greater than P naught A in the mole fraction of A. PB is greater than P naught B in the mole fraction of B. Everything is higher here. So we call it as positive deviation. Positive deviation. So in a positive deviation, hydrogen bond is broken. Endothermic process, delta H mixing is greater than 0. Molecules occupy more space. Delta V mixing is greater than 0. Molecules are easily moving to the vapor phase. So PA greater than P naught A in the mole fraction of A. PB greater than P naught B in the mole fraction of B here. So everything is positive here. But only one thing is going to decrease here because it's an endothermic process. So energy is absorbed from the surrounding. So system takes the energy from the surrounding. So the temperature of the solution will decrease here. Temperature of the solution decreases. That's only one going down here. Temperature decreases. Remaining delta H mixing increases. Delta V mixing increases. Partial vapors of A and B also increases here. Now let us see the graph for ideal gas, non-ideal gas solution. showing positive deviation. The dotted line shows for the ideal solution. The dotted line shows for the ideal solution. The curved line is for the non-ideal solution showing positive deviation. So everything you can see above the dotted line, positive deviation. Above the dotted line, we are seeing here same thing. X-axis mole fraction, Y-axis vapor pressure. Left extreme, mole fraction of A is 1, so P naught A shown in the Y-axis. Right extreme, P naught B, mole fraction of B is 1 here. How it is shown, changing is shown with the mole fraction. Dotted line for an ideal solution, curved line for a non-ideal solution. The curves are higher than the dotted line because it's a positive deviation. It's a positive deviation. Graph is very important. Sometimes I ask you to draw the graph for a positive deviation. Or in the multiple choice question, they may give 3 or 4 graphs. They will ask you which one is representing positive deviation, or which one is representing ideal solution, or which is representing non-ideal solution. Now let us see the maximum in this curve, which shows the P total. I'm taking P total, maximum in the curve. I'm going here. Let us say it's maximum here, right? This is maximum vapor pressure. Maximum vapor pressure. This point is called as azeotrope. You'll see later. This point is known as azeotrope. Maximum in the curve forms azeotrope here, right? Azeotrope is constant boiling mixture without any change in its composition. Later we'll see that in detail. So this is azeotrope here. Positive deviation we are seeing. I'll go for the negative deviation. Here a bond formation, new bond formation is taking place. So I take an acetone and chloroform I am taking. So a hydrogen bond is formed between the proton of chloroform and lone pair of electron on oxygen in acetone. Lone pair of electron on oxygen in acetone. A kind of attraction developed here that results in hydrogen bond formation. So here hydrogen bond is formed here. When a bond is formed, energy is released here. When a bond is formed, energy is released. Exothermic reaction, delta H mixing is greater than 0. Now because of the bond formation, molecules cannot move freely. It occupies lesser space. Delta V mixing is less than 0 here. Delta V mixing is less than 0. And of course, now the molecule cannot move to the vapor phase easily. So PA is less than P naught A into mole fraction of A. PB is less than P naught B into mole fraction of B. This is negative deviation. Negative deviation because of the hydrogen bond formation, exothermic reaction. So everything is decreasing here. But it's an exothermic reaction. That is, energy is given out by the system to the surrounding. So temperature of solution increases here. Right. Okay. This is negative deviation. One more example you can take by mixing two solvents, aniline and phenol here. See, for example, I have taken phenol, C6H5OH. Right? Another molecule of phenol, C6H5OH, and so on here, OH. So between lone pair of electron on oxygen and a proton of phenol, a hydrogen bond is formed. This is intermolecular hydrogen bonding. Intermolecular hydrogen bonding is formed. Same aniline I am taking. This also forms intermolecular hydrogen bonding, NH2. Another aniline molecule. Right. Lone pair is here, NH2. Hydrogen bonding is formed. So both phenol and aniline form the hydrogen bonding. Both phenol and aniline form the hydrogen bonding. I am mixing both phenol and aniline to form a solution. Of course, they do not react with each other. So I take in phenol, C6H5OH. Phenol is taken. Then I am taking aniline, C6H5NH2 here. Aniline I have taken C6H5NH2. Right? Sorry, NH I can write here. 1 minute. Right. Now I'm taking NH2 here. Okay. Now I've taken OH and NH2 I have taken here. Right. Now I'm mixing it together. Let us see how the bond is formed there. Right. So I've taken OH. So proton of phenol. And then aniline NH2 I have taken. Proton of phenol is there. O minus H plus here. Aniline, lone pair of electron is there. Aniline, nitrogen has got a lone pair of electron. Hydrogen bond formation taking place. When I mix phenol and aniline, hydrogen bond formation takes place between the proton of phenol and lone pair of electron of nitrogen and aniline. This hydrogen bonding is stronger. Hydrogen bond formed between phenol and aniline is stronger than the hydrogen bond formed in phenol or the hydrogen bond formed in aniline. When I compare these strengths here, the hydrogen bond formed between phenol and aniline in the solution is stronger than the hydrogen bond formed by either phenol or by aniline here. So it shows a negative deviation. The negative deviation curve is shown here. X-axis mole fraction, Y-axis vapor pressure, and we have seen the dotted line shows the ideal solution. The curved line shows the non-ideal solution, showing a negative deviation. It is below the dotted line here, because it's a negative deviation. I'm going for the minimum here. I'm going for the minimum now. So this is the minimum value. This forms an azeotrope here. Azeotrope. Okay. So negative deviation, everything is decreasing less here, but the temperature of the solution will increase. The temperature of the solution will increase. That is negative deviation, right? Okay. Now let's see what is azeotrope. Azeotrope are the binary mixtures. That is, I'm combining two solvents to give a mixture having the same composition in liquid and vapor phase. The composition in liquid and vapor phase is same. That's called as azeotrope. Are the binary mixtures having the same composition in liquid and vapor phase here. And then they boil at a particular temperature or at a constant temperature without any change in its composition. We have seen positive deviation, maximum vapor pressure. Like this, we have seen a graph like this. It goes. This is positive deviation, maximum vapor pressure. So boiling point will be minimum here. The boiling point will be minimum because boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. So the boiling point is minimum here. We'll just see once again and show you for a positive deviation. So this is what? Maximum vapor pressure azeotrope. So here the boiling point is minimum. So it forms a minimum boiling azeotrope here. Minimum boiling azeotrope. Same way, negative deviation azeotrope is minimum. You see here the vapor pressure is minimum. So the boiling point will be maximum here. Negative deviation forms a maximum boiling azeotrope. Right? Positive deviation, minimum boiling azeotrope. Negative deviation, maximum boiling azeotrope here. Example of minimum boiling azeotrope is 95% by volume of ethanol, 5% by volume of water. That is the reason why when I say I want to remove all the water, I want to get 100% ethanol, 100% alcohol by fractional distillation. I can only get up to 95% volume of ethanol here. 5% water I cannot remove here. 5% by volume of water I cannot remove because it is forming an azeotrope mixture here. It will boil without any change in its composition here. The whole solution will boil without any change in its composition. It will be like a single liquid now. That is the reason why fractional distillation cannot be used to get 100% ethanol. I can go up to 95%. Then I'll add some chemicals to remove the remaining water. Some agent which can absorb water molecule. I can add some agent which can absorb water molecule to make it 100% ethanol. Then negative deviation example, maximum boiling azeotrope, 68% by mass of nitric acid and 32% by mass of water. Azeotrope boils off with no change in its composition. Therefore, their components cannot be separated by fractional distillation. I mean, I can go only up to 68% by mass of nitric acid, or I can go up to only 95% by volume of ethanol. Right. Next class, we will do the numerical based on Raoult's law. Thank you. This is from Yashil Academy, given by Srinivas Vasudeva.